Today we are going to factor polynomials. We've factored in the past, but we've only dealt with quadratic equations. Today we're going to deal with quite a bit more than that. Okay, so we are going to rely heavily on you kind of already knowing how to factor certain quadratic equations, though there will be some review for us all. Okay, one learning target. I can factor polynomials that have 2, 3, and 4 terms. Okay, and to be able to make that happen, I have created a nice cheat sheet for us, which you should all already have. Okay, and this cheat sheet in this upper left-hand corner is going to diagram a flow chart of exactly what method to use. Okay, so you're going to need to know all of these different methods. Okay, and you need to know when to use them, and when to use them is diagrammed onto our cheat sheet. Okay, so when we look at this, you have to identify how many terms there are, and then once you figure out how many terms there are, sometimes you have to answer a question. Okay, and that will help you determine what method that you should be able to use. Okay, so we are going to consider a polynomial with integer coefficients completely factored when it's written as a product of unfactorable polynomials, again with integer coefficients. So let's go ahead and take a look at here. So we're going to talk about our special patterns. So if I were to do this, the first thing I would ask myself is there a greatest common factor? Okay, so we're going to look at the very first one here. 16x squared minus 81. Okay, so I'm looking, there is not a greatest common factor when it in terms of variables, right? One has x squared, the other one has no x at all. So then I want to start looking about numbers. Is there a number that is going to divide out of 16 and 81? So 16, 4, 4, 8, and 2, as well as 16. And none of those numbers divide into this, so there's no greatest common factor. Okay, so then you want to ask yourself, how many terms are there? Okay, when there's 2 terms, so 1, 2 terms. Okay, and that tells me I'm going to use one of these 3 special patterns. Okay, so we have to figure out whether it's a difference of squares, a difference of cubes, or a sum of cubes. Those are the 3 different ones we're going to have. And we're going to start with the difference of squares. Here's the pattern that will be given to you on your cheat sheet. Okay, that you will need to know how to use. Okay, and that there is diagramming when you have a perfect square and you're subtracting a second perfect square. So you need to know what your perfect squares are. Okay, and here I have another on the back of that exact same cheat sheet. I have a list of all the roots. So just like your first 15 whole numbers, they're perfect squares and they're perfect cubes. So for example, the perfect square of 2 is 4 and the cube of 2 is 8. Okay, and so if I want 7 squared is 49. If I want 7 cubed, it's 343. I did the exact same thing with the handful of the first variables. Okay, so if I want to know x to the third's perfect square, it's x to the 6th. If I want to know x to the third's perfect cube, it's x to the 9th. Okay, so we can go ahead and look here. So we're going to take a look and ask ourselves, is 16x squared a perfect square? And then also, is 81 a perfect square? Well, as I look down my square column, I see 16. Okay, I also see 81. So as far as these numbers go, they are perfect squares. Okay, what about x squared? Is x squared a perfect square? Yes, it is. It's in my perfect square column, and its root is x. So what I'm going to redo is I'm going to rewrite this problem, okay, with 2 roots, and I'm going to raise that to a power. So what's the 16x squared? What's the root of that? Well, what's the root of 16 squared? Okay, or of 16? It is 4. Okay, so this here is 4, and what's the root of x squared? It's x. All right, and then what's the root of 81? Well, the root of 81 is just 9. Okay, and you can see all of this on your chart. Okay, so as I'm looking at here's 81, its root is 9. Here is 16, its root is 4. Okay, so what does this do for me? Well, what this does is it gives me an a value. So now I have like an a value of 4x and a b value of 9. So then I can just write this pattern. Okay, this factors into a plus b times a minus b. So we're going to factor it into a, 4x, plus b, plus 9, times 4x, a, minus b, 9. And that's just what it factors into. We've actually taught this exact same factoring method back into Chapter 4. Okay, everybody take a moment, try this second one of difference of squares on your own. Okay, so you're asking whether these are perfect squares or not. Okay, we're asking whether 9x is a perfect square. It is. Its root is 3x. Then we're going to ask ourselves whether 25 is a perfect square. Yes, its root is 5. Okay, so now I have my a value, which is 3x, and my b value, which is 5. So this is going to factor into a plus b, so 3x plus 5, times a minus b, 3x minus 5. Okay, that is difference of squares. So as you're looking at your cheat sheet, of all of these different methods, you now have the first one right here. This one checked off. You know how to do that. Okay, so I'm going to actually just highlight this in red. We have this method accomplished. Okay, let's go do difference of cubes. We're going to look at difference of cubes, and the concept is really the same. We know a difference of cubes is a perfect cube subtracted from another perfect cube. So you want to ask yourself whether or not 27x cubed is a perfect cube and whether 8 is a perfect cube. Okay, so as I look at this, well, 27x cubed. I know the root of 27 is 3, and again, we can check that on our cube and square cheat sheet. So 27 is a perfect cube, and its root is 3. Okay, so I can rewrite 27x cubed as 3x, that whole thing to the third power. Okay, and then I can write 8 as a root, 2, again to the third power. You can find 8 and 27 in the cube column. Okay, so now I have an a value, which is 3x, and a b value, which is 2. Okay, and so now what I can do is I can just go ahead and fill in these pieces. Okay, so it's going to start with a minus b, so 3x minus 2, times a squared, so I have to square a, plus a times b, plus a times b, a times b, plus b squared, which is just 2 squared. Okay, and then now I can just simplify this. So this is going to be 3x minus 2 times 9x squared plus 6x plus 4. Okay, and the one thing about the difference of cubes and sum of cubes is this second trinomial that we get, 9x squared plus 6x plus 4. If you've done everything right, that part should be unfactorable. So what does that mean? That means that this is just my final answer right here. Okay, why doesn't everybody take a moment and try the one on the right? Okay, x cubed is a perfect cube. Its root is x. And then 64 is a perfect cube. Its root is 8. Meaning I have an a value of x and a b value of 8. So I can go ahead and plug it in. So a minus b, so x minus 8, times a squared, so x squared, plus a times b, plus a times b. I'm just going to write that as 8x. And then plus b squared, which is 8 squared. Okay, we're lucky and x squared is just simplified. And then 8 squared is 64. Okay, and that is the difference of cubes factoring. Okay, So we now have two of our methods over and done with. Okay, lastly, there's a sum of cubes. Okay, there is no sum of squares, but there is a sum of cubes. Okay, and so let me adjust this a bit. Okay, there is a sum of cubes, but there's not a sum of squares. Okay, so we can go ahead and follow our flow chart here, because our flow chart does start us off with something very important. And the very important thing is you always have to take the greatest common factor out first. Okay, so as I look at this, I'm looking at 8 and 64, and I'm identifying that they all divide by 8. So that means I can factor an 8 out first. Okay, so then I get 8 times the quantity of x cubed plus 8. Okay, and then I'm seeing that x cubed is a perfect square, or perfect cube. And I'm seeing that 8 is also a perfect cube. So that means I can go ahead and start this problem. So, or factoring this problem. Okay, the root of x cubed is x, and the root of 8 is 2. So that means I have an a value of x and a b value of 2. So I can go ahead and follow this pattern that's here. A plus b, so x plus 2, times a squared, so x squared, minus a times b, minus a times b, so I'm going to go minus 2x here. And then plus b squared, so plus b squared. Okay, and then all I have to do is simplify this. And 2 squared is 4. And that's just my answer. Okay, pause the video and go ahead and try this one now. So I'm assuming you've already tried this. So I'm looking at 64x cubed. Okay, and 64's root is 4, and 125's root is 5. So that means I can rewrite this as 4x cubed plus 5 cubed. So it is a sum of cubes because it's a perfect cube added with another perfect cube. Meaning my a value here is 4x and my b value here is 5. Okay, so I can go ahead a plus b, so 4x plus 5, times a squared, so 4x squared, minus a times b, 4x times 5, plus b squared. Okay, and so then this is just going to need to be simplified for the same reason this one needed to be simplified. Okay, so we have 4x plus 5, 16x squared, because 4 squared is 16, x squared is x squared. 4x times 5 is 20x, and then plus 25. Okay, and again, if you do the formula correct, you do not, or this back part will just not be able to be factored. Okay. I'm going to go ahead and highlight this in red here, or outline, I mean. Okay, because we officially have all of the 2 special patterns. Okay, so anytime you're doing your work and you need to factor something that has 2 terms, these are our only methods. Okay, so feel free to use this sheet as much as you can. And those are our 3 methods, and then they're also outlined up over here. Okay, let's move on to the next page. All right, so now what we have to do is we have to identify that these problems often are going to have a greatest common factor. Okay, and we need to take out the greatest common factor in order to just actually be able to factor this. Okay, and a lot of these become, they boil down into problems we've done in the past. So I'm looking at 10x cubed minus 35x plus 30. This is number 1 here. Okay, and I want to factor this completely, meaning I want to factor it in its entirety all the way down until nothing can be taken out or can be factored out any further. Okay, so as we check our sheet, okay, our sheet tells us to always take out the greatest common factor. So let's go ahead and do that. We're looking for a value that divides evenly out of all of these. Well, to me, 5 is the first thing that's jumping off this paper. Okay, we're going to take 5, but there's something else. They each have a common variable of x. So since they each have a common variable of x, I can actually take a 5x out of each of these. Okay, so if I take 5x out of this, I'm going to get 2x squared left over. 10 divided by 5 is 2. X cubed divided by x is x squared. Okay, negative 35 divided by 5 is negative 7. X squared divided by x is x. 30 divided by 5 is 6. And then x divided by x is 1, so it's just 6. Okay, so that's the first thing that we did, is we took out the greatest common factor. Okay, so now I have taken out the greatest common factor, and I want to ask myself, how many terms do I have? Okay, so it looks here, 1, 2, 3. I have 3 terms. The question I need to answer now is, does my a value equal 1? Okay, does my a value equal 1? The answer to that is no. And so we are going to go ahead and review the Xbox method. Okay, so this is the one we're going to do right now. Xbox method of factoring, which this is review. Okay, so as I look at this, I'm going to factor, and I make my x, and I put my a times c value here, which is 12. And then I'm going to put my b value here, which is negative 7. I'm looking for the numbers that multiply to 12 and add to negative 7. So that's going to be negative 3 and negative 4. Okay, after that, I can set up my box. Okay, you're going to put your ax squared term here, so you're going to put 2x squared. You're going to put your c value here, which is 6. So then we take a negative 3x here and a negative 4x here. Okay, and so now what we're really doing is we need to figure out where I take my negatives out. If you look in the bottom right-hand corner of your cheat sheet, it reminds you where to take negatives out. I have negatives in each corner, so I'm going to take a negative out here, and I'm going to take a negative out here. Okay, so what's the greatest? And then I start taking greatest common factor out horizontally and vertically. Okay, greatest common factor here is 2. Greatest common factor here is x. Greatest common factor here is 2 and an x. Greatest common factor here is 3. So what does this factor into? This factors into 5x times 2x minus 3 times x minus 2. Okay, each of these terms, so now I can check each of these terms whether they can be factored, right? And so I would just go back through my flowchart. How many terms are there? There's 2. And I have to identify them as a special pattern. I'm looking at this. This is not a special pattern, and neither is this, meaning we're done. Okay, let's do number 2. Number 2, I have 8x to the 4th minus 18x squared. Okay, my factor thing says I need to start with the greatest common factor. So I'm looking at this, and I can identify 2 divides evenly out of each of these. Okay, but they each have at least an x squared in it. So that means that x squared is indeed a factor. So we can take out an x squared. When I take out an x squared, I have 8 divided by 2 is 4. X squared, or x to the 4th divided by x squared, is x squared. Then I can go ahead and 18 divided by 2 is 9. X squared divided by x squared is 1, so 9 times 1 is 9. Okay, so now I've taken out the greatest common factor. I can go ahead and identify how many terms are there. Well, for us, there's 2 terms, and I need to check for special patterns. Okay, so here I have 2 terms. I have 4x squared and minus 9. Okay, that's kind of hinting off to me that I'm going to use a difference of squares, because 4 is a perfect square, x squared is a perfect square, and 9 is a perfect square. So this can factor into 2x squared times, well, the root of 4x squared is 2x, and the root of 9 is 3. Okay, so this factors into 2x squared times 2x plus 3 times 2x minus 3. Okay, there are two terms left over, but none of them are any of our special patterns, meaning, again, we are done. Okay, let's look at number 3. Number 3, I have 3 terms, but I want to check for a greatest common factor. So I'm identifying that a 2 divides out of each of these, and they all at least have an x cubed in them, right? This has an x cubed, this has an x cubed and an x, this has an x cubed and an x squared. So I can go ahead and take an x cubed out. Okay, and so if I take a 2x cubed divided out of this, so 2 divided by 2 is 1, x to the 5th divided by x to the 3rd is x squared. 8 divided by 2 is 4. X to the 4th divided by x cubed is x. 8 divided by 2 is 2, or is 4. And x cubed divided by x cubed is 1. 4 times 1 is 4. Okay, so now I've taken out my greatest common factor, and I can go ahead and just start using my chart. I have 3 terms. Is my a value 1? In this situation, yes, it is. It is 1. Yes. So we are going to go ahead and use the multiply to c and add to b method. Again, this is entirely review. Okay, so this is review. So we already know how to do this, but here's your reminder. Okay, so when I'm doing this, I'm just looking for numbers that multiply to 4, this 4, and add to 4, this 4. So what numbers are going to multiply to 4 and add to 4? Well, hopefully you're identifying that as 2 and 2. So we can go ahead and say that this is x cubed times x plus 2 times x plus 2. But if you recall from previous sections, I have a factor that's repeating itself. X plus 2 is repeating itself. So I can actually condense that down into one term. X plus 2 times x plus 2 is x plus 2 squared, for the same reason that 4 times 4 is 4 squared. Okay, so these are the fundamental things that you're going to need to be able to do to be successful through the entirety of this chapter. Okay, is problems exactly like this. So what I want everybody to do is take a moment, pause the video, try A, B, and C on your own. Notice that A, B, and C are not in the same order as 1, 2, and 3. You have to try to identify what method you're going to use on your own. Okay, so pause the video and try that and check in with me right now when you are done. So I'm looking at A. Okay, and I want to take a greatest common factor out. Out of 18 and 32. So if I take a 2 out of each of those, I get 9 and 16. Okay, so each of these can have 2 parts taken out of it, because I could take a 2 out of each of these numbers, but they each have an x cubed at least in it, so I can go ahead and take an x cubed out. So 18x to the 5th divided by 2x to the 3rd is going to be 9x squared, and 32x cubed divided by 2x cubed is just 16. I have 2 terms, so I have to use special patterns, and I identify 9 and 16 as perfect squares. So I'm going to go ahead and factor this using a difference of squares. The root of 9x squared is 3x, and the root of 16 is 4. So this is going to factor into 2x cubed times 3x plus 4 times 3x minus 4. And that's it. Okay, letter B. Letter B, I'm identifying 4 and an x as the greatest common factor. 4 divides into each of these numbers. X divides out of each of these variables. So I'm going to take a 4x out. And when I take a 4x out, I get x squared plus 2x plus 1. Okay, I have 3 terms, and my a value is 1. That's telling me to use the multiply to c, add to b method. So I'm looking for numbers that multiply to 1, but add to 2. Hopefully you've identified those numbers as positive 1 and positive 1. So this factors into x plus 1 times x plus 1. I have repeated factors, so then this can factor into 4x times x plus 1 squared. Okay. C. I'm identifying a 3 divides into each of these, and x to the 4th divides out of each of these also. So I'm going to go ahead and divide a 3x to the 4th out. Okay, 9 divided by 3 is 3. X to the 6th divided by x to the 4th is x to the 2nd. Negative 3 divided by 3 is negative 1. X to the 5th divided by x to the 4th is x. Negative 6 divided by 3 is negative 2. X to the 4th divided by x to the 4th is 1, so that's just it. Okay, so that's my greatest common factor. Okay, after that, I have 3 terms, but my a value is not 1. So if you're following your flow chart, 3 terms a value of not equal to 1, okay, we have to use the Xbox method. So a times c is going to go here, so 3 times negative 2 is negative 6. And my b value is going to be negative 1. Okay, I have to find the numbers that multiply to negative 3 or negative 6 but add to negative 1. That's going to be negative 3 and positive 2. Then I can use the box. My ax squared term goes here. My c value goes here. And then my sides of my x go here. Okay. If you look at your cheat sheet in the bottom right-hand corner, you're going to identify that my negative is going to come out here or wherever you have your 2 negatives in a row. Then I just take the greatest common factor out. 2 and 2x has a common factor of 2. 3x and 3x squared has a common factor of 3x. 3x squared and 2x have a common factor of x. And 3x and negative 2 are going to have a common factor of negative 1. So this is going to factor into 3x to the 4th times x minus 1 times 3x plus 2. Okay. That is A, B, and C. So hopefully you all did well, and if you didn't, you figured out what you did wrong. Okay. Now what we're going to do is we're going to factor by grouping. But in recent years, I have identified that factoring by grouping can also be done by just the regular box method, which I'm going to choose to do here because the regular box method is the exact same as what we do in the Xbox method, except for we don't have to do the X. Okay, so let's take a look at our factor chart here. Okay, so the first thing we want to do is we want to go ahead and take the greatest common factor out first. Okay, so greatest common factor between 1, 5, negative 4, and negative 20. There is no greatest common factor. The only number that divides out of all that is 1. Also, they don't all have a variable in it, so there's no greatest common factor there. Okay, so then I'm going to ask the question, how many terms are there? 1, 2, 3, 4. So there's 4 terms. Okay, ax cubed plus bx plus c plus d. You have to answer the question, does b divided by a equal d divided by c? So here, my a value would be 1, my b value would be 5, my c value would be negative 4, and my d value would be equal to negative 20 in this situation. Okay, so then I want to ask myself, does b over a, 5 over 1, is that equal to d over c, negative 20 over negative 5? Well, let's check. Okay, so hopefully we don't have to do 5 divided by 1, but it is 5. And so negative 20 divided by negative 5. Or negative 4. I miswrote something here. This should be negative 4. Okay. Negative 20 divided by negative 4. That's also 5. So all of these are equal to 5. Since they're all equal to the same number, this is going to tell you to use the box method. Okay, so let's get our little cheat sheet out. Box and Xbox are super similar to each other. They're almost the same thing. Actually, box method's a little bit easier. Okay, so I'm about to teach you this box method. So if you look at our flowchart, we have 3, 4, 5, 6, 7, 8 methods, and we're already going to have 6 of them figured out just by the end of today. Okay, so let's go ahead and do the box method. Box method's very straightforward. It's very, very consistent with what we've done in the past. Okay, no x needed. Okay, so then here I have, you're just going to go ax cubed, or your a, I'm just going to put your a term, b term, c term, d term. So my a term is x cubed. This is 5x. This is negative 4x. And this is negative 20. Okay, just a, b, c, d. A's term, b term, c term, d term. Okay, you get to take a negative out in the same situation you would with your box, your Xbox method. We have 2 negatives in a row along the bottom here. So I'm going to take a negative out here. And then you just take the greatest common factor. Greatest common factor between negative 20 and 5x is 5. Greatest common factor between 4x and 3 and x cubed is x. Greatest common factor between x squared and 3x cubed is x squared. Okay, greatest common factor between 4x and 20 is 4. Okay, so this is what I have so far. And now, as I'm looking at this, hopefully you all are identifying something. Hopefully you all are identifying that this is a difference of squares. So this is where this chapter gets very, very, not confusing, but it can get tricky to some people, is that you can factor once, get a result out, like we just did, and it turns out part of that answer can be factored again. So let's go ahead and look. X plus 5, can that be factored again? Well, it's 2 terms, and so it has to follow a special pattern. Neither of these are a perfect square nor a perfect cube. That means x plus 5 is factored. But when I look at x squared minus 4, that is a special pattern. That's a difference of squares. X squared is a perfect square. 4 is a perfect square, and I am subtracting them. So I need to follow my difference of squares formula. Okay, so this is going to turn into x plus 5 times the root of x squared is x. The root of 4 is 2. And then this factors into x plus 5 times x plus 2 times x minus 2. And this is my final answer in its complete entirety. Okay, so this one required two different types of factoring. You had to do it more than once. Okay, let's do, take your time to do D on your own. So go ahead and pause the video and check it with me when you're done right now. So this one has some common factors. Like it appears as though they all have a, like these all have a 3, but this one does not. So I can just go ahead and get my A value, which is 3, my B value, which is 1, C value is 9, and my D value is 3. So I have to ask, is B over A the same as D over C? So is 1 over 3 the same as 3 over 9? And the question to that is yes. So we are going to be good to go using the box method. Okay, so let's go ahead and use the box method. Okay, so we're going to use 3x cubed, and then x squared, then 9x, and then 3. Greatest common factor here is 1. Greatest common factor here is 3. Greatest common factor here is a 3 and an x, so 3x. Greatest common factor here is 1, but also an x squared. So then I get 3x plus 1 times x squared plus 3. Okay, so then just like we did in the previous problem, we should check whether these can continue to be factored or not. So 3x plus 1, okay, it's 2 terms, but it's not a special pattern. None of those are perfect squares. None of those are perfect cubes. So 3x plus 1 is factored completely. What about x squared plus 3? Okay, it is 2 terms, so we got to look. Ooh, it could be a difference of squares, but there's 2 things wrong with this. One, we are adding. So difference means subtraction. So, you know, x squared is also a perfect square. But if we look at 3, 3 is not a perfect square, nor is 3 a perfect cube. So what does this mean about x squared plus 3? It means it's completely factored. Cannot be solved any further. This is its completely factored form. Okay. So what we're going to do now is we're going to deal with things that are in quadratic form. And any expression in the form a u squared plus bu plus c, where u is an algebraic expression, means that it can be factored in quadratic form. What that means is just because, for example, like on my cheat sheet, I have like x squared and bx. Just because it's x squared and bx doesn't mean that it only works for quadratics. It can work for higher degree as long as it follows this pattern. For example, no variable, a variable, and then this variable's exponent is twice whatever the b terms is. Okay, and we're just going to see that develop here kind of as we go. So if we look at this here, 16x to the fourth minus 81, well, I'm looking at this and I'm saying, okay, it could be a special pattern because 64 and 81 are perfect squares. Let's check if x to the fourth is a perfect square. So I'm going to get my cheat sheet out, and squares, x to the fourth is a perfect square, and its root is x squared. So what does that mean? That means that this is in quadratic form. It means it can be factored like a quadratic equation and in the form of a quadratic equation, but it's not a quadratic equation. It can just be treated as such. Okay, so this is a difference of squares. So we can go ahead and start factoring this. The root of 16x to the fourth is 4x squared. And then we can subtract 81. Well, 81's root is 9. So 16x to the fourth's root is 4x squared. And then 81's root is 9. So this can be factored into 4x squared plus 9 times 4x squared minus 9. Okay, and just like the previous problems, we always want to check, like I factored once, but it might be able to be factored again. So as I look at this, well, these are all perfect squares, but there's no sum of squares. So this one can't be factored. But this one here, these are all perfect squares. 4 is a perfect square, x squared is a perfect square, 9 is a perfect square, and we're subtracting. That quite literally is the difference of squares by definition, right? A perfect square subtracting another perfect square. So this can be factored again, though this cannot. So we're going to get 4x squared plus 9 times the root of 4x squared is 2x, and the root of 9 is 3. So that means this can be factored into 2x plus 3 times 2x minus 3. Okay, we've already determined this can't be factored. Neither are perfect squares nor perfect cubes. Neither of these are perfect squares nor perfect cubes. This line right here is this answer, or this thing completely factored out. Okay, so that's what it means to be in quadratic form. It's not a quadratic equation, because if it was a quadratic equation, it would have an exponent of 2. But it's in the form of a quadratic equation, so that means we can treat it as such. Okay, number 6. So number 6, as I'm looking at this, there's a greatest common factor. And the thing that's nice about all these problems is if there's a greatest common factor, you just factor that out right away. That's like, there's no exceptions to that rule. If there's a greatest common factor, you just need to take that out. So let's go ahead and do that. It looks like a 3 divides out of all of them, and also a p squared divides out of all of them. So I'm going to take a 3p squared out. That gives me p to the 6th. This gives me 5p to the 3rd. And this gives me 18 divided by 3. 3 is 6. Okay. So this is another one that's in quadratic form. Quadratic form, if it was quadratic, it would have an exponent of 2, exponent of 1, and then no exponent. This one has no exponent 3, and then double that into 6. So if this one's ever double, or if this one's ever half of this one, it's exponent, or this exponent's double of this one, and then there's no, that means you can just treat it like a regular quadratic. Meaning, we just look for numbers that multiply to 6 and add to 5. Because I have 3 terms and my a value is 1. So we're going to get 3p squared times p cubed plus 2 times p cubed plus 3. Okay. Because p cubed times p cubed is p to the 6. P times 3 is 3p. 2 times p cubed is 2p cubed. 3p cubed and 2p cubed are 5p cubed. 2 times 3 is 6. Okay, so then as I look at this, I want to check to see if this can be factored further. So I'm identifying p cubed as perfect cubes. So I just have to check whether 2 or 3 are perfect cubes. If I go to my perfect cube list, they're not on it, so they're not perfect cubes, meaning that this is completely factored. Okay. I want everybody to pause the video and try E and F on their own and check it with me right now. E's got a lot going on. It does have a greatest common factor of 2, but it looks like also x to the 5th. So I can take a 2x to the 5th out, and then that's x to the 8th is left over, because 8 and 5 is 13, and then 10 divided by 2 is 5, and then x to the 4th, and then 8 is, that's 4. Okay. So then this is in quadratic form because no exponent, 4 exponent, double that to 8. So this can be treated just like this one here. So we're going to go x to the 5th times numbers that multiply to 4 and add to 5 would be 4 and 1. So we're going to go x to the 4th plus 4 and x to the 4th plus 1. Okay, so now I want to check whether those can be factored further, because x to the 4th is a perfect square and 4 is a perfect square, but if you check your perfect square on your cheat sheet, it's only a difference of perfect squares, and we are subtracting, we are adding, so that means they can't be factored further. Okay, F, these values are very large, so we want to check whether there's a greatest common factor. One's divisible by 5, and the other's probably divisible by 4. Not really identifying a number that divides evenly out of each. So let's go and check and see if those numbers are perfect squares or cubes on our sheet. 625 is the first one I'm going to look at. Doesn't seem to be on it, so let's try 256. 256. I wonder if these ones are not on our sheet here. Okay. Well, 256 is a perfect square, and its root is 16. So I'm going to figure out what... Okay, so if I go... It turns out that this is a perfect square and this is a perfect square. Okay, I had to do a little bit of work here. Okay, but this one's root is 25. Okay, so we have 25x to the 4th squared. Then we're taking away 256, which is 16 squared. Okay, and so this is a difference of squares. A value equal to 25x to the 4th, and B value equal to 16. So that means I can go ahead and factor this further. So this is going to be factored into 25x to the 4th plus 16 times 25x to the 4th minus 16. Okay, well, these are perfect squares, 25 and 16. And so is x to the 4th, but there's no sum of squares. There's only a difference of squares. So that tells me this can be factored further because I have all perfect squares and I'm subtracting it. But this one is factored because there's no sum of squares. Okay, so we can go ahead and keep that as is. Okay, the root of 25x to the fourth is 5x squared. And the root of 16 is 4. So now I have another a value and another b value. Okay, so this is going to factor into 25x to the fourth plus 16 times 20, or not 25, 5x squared plus 4 times 5x squared minus 4. Okay, 5's not a perfect square, so this isn't a perfect square. It's not a perfect cube either, so this is its answer completely factored out. All right. Let's move on. I think this is the last page. Okay. A polynomial f of x has a factor has a factor x minus k only if f of k is equal to 0. Okay? So this is exactly what we were talking about at the very end of 4.3. So if 4.3, this is kind of going to be the beginning of our synthetic division to solve. So if we refer back to that, in theory I'll be able to find the notes to that. If you recall, we were able to use synthetic division, and when we divided, if the remainder was 0, we got a result. Okay? So what we can do is we can actually use that information to factor. Okay? And we're going to really hammer this in 4.5. So if you're not picking up exactly what I'm saying yet today, give it some time. If I divide this by x plus 2, which I did using synthetic division, I get this. Okay? So really what that means is I now have this. 2x squared minus 3x minus 5, and then that times x plus 2. That is my result to get to this. Okay? So what I have here is I have another term here. This term right here may or may not be able to be factored. And if it can be factored, we can factor that more. So we can use synthetic division to divide out parts of our polynomials to get a result, and then take that result and try to factor that further. Let's see what that looks like. Okay. So what does that mean? We want to show that x plus 3 is a factor. So that means we can use synthetic division. Okay. So we are actually, I'm not going to do all the way. I'm only going to do half, because we are not going to be all the way down the synthetic division to 4 terms. But we'll be pretty close. We're going to do about half, because we'll have a little bit of it now. We'll spend the rest of 4.5 doing exactly this, and then we'll move on. Okay, so we want to show that it is a factor. So if you recall, we want to show that x minus 3 is a factor. So you're going to take the value that makes this 0, which would be negative 3, and we put it in here into our upside down division. 1, 3. I'm missing the x squared term, so I got to put a 0. Negative 1, negative 3. Okay, bring that down, and we get 1. And then negative 3 times 1 is negative 3. That's 0. And then that is also 0. So that's 0. That's 0. This is negative 1. Negative 3 times negative 1 is 3. So we get 0. So what does this mean? I have a remainder. I have a constant. I have an x. I have an x squared. And I have an x cubed. So I just divided this out, and I showed that this is indeed a factor because this value is 0. Okay, so since this value is 0, okay, I can go ahead and, or since the remainder is 0, I can rewrite this, whatever this is, times my factor. So we can go x plus 3 times x cubed minus 1. Okay, so then now I can check x plus 3 can't be factored further, but if you look at x cubed minus 1, that can be factored further because 1 is a perfect cube, its root is 1, and x cubed is a perfect cube. So this is a difference of cubes. Okay, so we have x plus 3 times x to the third minus 1 to the third, where my a value is x and my b value is 1. So we can go ahead and plug this into our formula, which I have right in front of me because I do not have it memorized, so I would expect you all to do the same. So we're going to go x plus 3 times x minus 1 times x squared plus a times b, so x times 1, or just x, plus 1 squared, which is just 1. All right, so this here is the completely factored version of this. Okay, and we started factoring by using synthetic division. Okay, and this is going to be a very important method for us moving forward. But for the time being, we only have this concept like half there. Okay, like we're just starting to introduce that concept. Okay, I want you all to try to divide this by synthetic division. Okay, and then go ahead and see if you can factor beyond that. Okay, so what does this mean? So I'm looking for the value that makes this 0, so that's going to be 2. And so then we can put 1, negative 2. We can't forget about the x squared term. It appears to be gone. Okay. So then we can drop this down to get 1. 2 times 1 is 2. That's 0. 2 times 0 is 0. That's 0. 2 times 0 is 0. That's 1. 2 times 1 is 2. That's 0. This is my remainder, constant, x squared, x cubed. So this factors. This factors into x minus 2, because that's the factor that we just took out, times x cubed plus 1. Okay, this is a sum of cubes, which can be factored further. So we get x minus 2 times the root of x cubed is x. The root of 1 is 1. So we have an a value of 1 and a b value of 1. Or an a value of x and a b value of 1. Meaning this is x minus 2 times a plus b, so x plus 1, times a squared, so x squared, minus a times b, so just x, plus b squared, which is just 1. So this is what it factors into completely. Turns out if you look at these problems, b over a is the same as d over c. b over a is the same as d over c. So you could have used the box method here to solve it. And actually, in general, I would suggest that. But this is just the first hint at seeing how synthetic division can help us factor. And actually, it's a big part of factoring moving forward. Okay, during the first 5 seconds of a roller coaster ride, the function h of t is equal to 4t squared minus 21t squared plus 9t plus 34. And it represents the height of the roller coaster after t seconds. So this is my t in time, and this is my height as a function of my time. How long is the roller coaster at or below ground level in the first 5 seconds? If you recall from chapter 4, we know that essentially we're just trying to figure out the values at which when we factor, those are and solve, those are where it is equal to 0. So this can actually help us solve equations, right? We want to know, when is this height at 0? Okay, so let's take a look here. So if I go ahead and take 34 over 9 and 21 over 4, those are not the same number. Okay, so what we can go ahead and do is we just want to know, like, the height is 0, right? So we would like to know, like, what are these values here? Okay, and those values are going to be the ones that help us identify like when it is at or below ground, because this is like the crossing point from above ground into below ground, or below ground into above ground. Okay. T seconds. How long is the roller coaster at or below? Okay. How long? Okay. I was thinking the question asked how many times is it above? Well, twice, or below once, because it's below once. But anyway. Okay, so what we can go ahead and do is we want to go ahead and we're just going to type this into the calculator. All right. So we are going to go ahead and go 4. And then we have to use x because we don't have t as a variable. T cubed minus 21t squared plus 9t plus 34. Okay, so our graph is real weird looking. Doesn't look quite like this. So let's think. We have a y-intercept here of 34, and we're only looking in the first 5 seconds. So let's go ahead and change the window. Okay, we don't really need to see the x's as negative, so that can be 0. And we know that we're only interested in the first 5 seconds, so we can go ahead and say our x is 0 to 5. So all I did was set my graph from 0 to 5. Okay, then we know it has a y-intercept of about 34. Okay, since it has a y-intercept of about 34, doesn't look like we have to go very far above that, so let's go. But we do want to see below ground, right? So let's go -10 to 40, just to be on the safe side here. Okay, now we're getting the similar picture to the graph. And I just want to know how much time is here, and then how much time is here. Okay, so we want to figure out where this value is, so we want to figure out where this crosses the x-axis. If you recall from chapter 3, which is quite some time ago, okay, if you want to, we hit second, and then you go to trace. And if you want to find where it hits the y or the x-axis, that's actually 0. So we're going to go to 0, and we are going to go to the left of that value. Okay, so we're still in the negatives, as you can see in the y values. We're still in the negative, so I'm not to the left of this point yet. Okay, so we're going to get, okay, now we're positive, so I'm going to hit enter. Now I have to get to the right of that spot, okay, which I am now. Hit enter again, and then you have to enter one more time for it to guess. Okay, after 2 seconds. So right here to here is 2 seconds. So this is x is 2. Okay, and so then now I want to do the exact same thing here, but for the other spot. Going slow, but I'm getting there. You can see the y values are starting to increase. Okay, so I'm to the left of this spot here because I'm down in the negative. Then I have to get to the right of it. Y value's in the positive, and then it can guess for me. 4.25. Okay, that's 4.25 seconds. So this is 2.25 seconds. Okay. So, what does this mean? This means how long is the roller coaster at or below ground in the first 5 seconds. So, it is at or below ground between 4.25 and 2, meaning that it is at or below ground for 2.25 seconds. Okay, and what that ends up being is you see these values here. Those are the values that make it at equal to 0. You're going to find out that these here end up being factors. Okay, so because those are the x values where the function is at 0. So we could actually just go ahead and use synthetic division, and we could factor this. Okay, and this is going to be a hint into the next section. Okay. Because when we have 4 terms, we would normally check the only method we really have is, does b over a equal d over c? Well, when that answer is no, we have to use synthetic division because 21 over 4 is not the same as 34 over 9. So we could divide this out by 2. So we can divide a 2 out, or an x minus 2 is really what we would do. To get 4, negative 21, 9, and 34. Okay, so let's go ahead and check. So we would drop this down to get 4. 2 times 4 is 8. Okay, and then we would have to go negative 21 plus 8. It's negative 13. And this would be negative 26. This would be negative 17. And this would be 0. And so then this would be 0. So this, or no, this would be 34. And then this would be 0. So then we have a remainder, a constant, an x, and an x squared term. So we just factored out x minus 2 because 2 is the value that makes that 0. Okay. So as you can see, that it turned out it was a factor because that's where it crossed the x-axis at. Okay, and that is going to be a nice hint. We're not going to factor this completely, although we could from this point on. But what we're going to do is we're going to use that as a little bit of a hint into where we're going for next chapter.